part C.2, verify Fibonacci formula, special cases. All right, so right now, this is a magic formula. How do you know it is correct? So we need to verify it. To verify it, how can you exhaust, or how can you prove it is true for all n greater or equal to 0? For n with small numbers, you can verify easily, but nobody can exhaust all those n numbers. Yeah. So I think at this point, some of you can connect to mathematical induction. Yeah. That's our tool. Yeah. We used that before. Yeah. We will use it many, many times. This is a powerful tool, so we will use it another time. Yeah. All right. To use the mathematical induction, first we apply it on some base cases. So let's start with the first base case when n equal to 0. Yeah, so that, because this one is 0, 1, 1, 1 minus 1, 0, right? Yeah, phi to the 0th power, 1. Yeah, it is 1. Yeah, so that is very simple, this case. But we need to verify another base case. Remember, n greater or equal to 2. This formula is correct when n greater or equal to 2. So we need to verify these two base cases. Then, after n greater or equal to 2, we can apply this recurrence relation. So that's why we need to do another one. Yeah. This time, after we plug in n equals 1, yeah, that's this case. Yeah. All right, to find the answer, the second term, a little more complicated. So we want to do some transformation on it. Okay? The way we do it, rationalize its denominator. Denominator is not a rational number. Yeah. So we can do it. So if you know the trick, yeah. So that's the basic way people use to make it simpler. So we divide by, conjugate, right? So, sometimes people call conjugate. The same non-zero number, both numerator, denominator, right? So then we simplify it, a plus b, we use this formula. Yeah. A minus b, okay, equals a squared minus b squared. The difference of squares formula, we use this, okay? So 1 minus 5, right? Negative, yeah, negative, it's okay. 2, 1 minus root 5, okay? So minus 4, 2, cancellation, negative, but we can switch the position of these two, right? So 2 root 5 minus 1. So that's this number, okay? Yeah. So that's the basic algebra skill you need to have. Yeah. Otherwise, it will be very hard. So you have to have some basic algebra skills. All right, so here we use that. Okay, I'll show you the details. So this, when you replace the circle by this new expression, you can see minus 1 plus 1 cancel out. Root 5 twice, then twice you can cancel out that 2. So root 5, another cancellation, you get 1, right? So you get a 1. Yeah. All right. So you verify the first two. For mathematical induction, these two base cases are already enough. So we can do the we can do the induction assumption, then step 3 to the proof. Yeah. But here, I want to do a few more verifications. The reason is I want to practice algebra scales. For this class, the basic algebra scales, so important. When we have a chance, we should practice it. So here, let's do a few more verifications to practice our algebra scales. All right? Yeah. Let's do next one. N equals 2 this time. How do we find the value of this expression? Yeah. Let us plug in those values. But the second term, we already did the form change. So let us use it just directly. We do not need to repeat it, right? We know it's correct. So let us just use it. Okay? Next, let us expand. So I hope you know the formula. Okay? A plus B square formula. A minus B square formula. So here, AB, yeah, we have that situation. All right? Yeah. So the denominator, both for the numerator, A square, remember the formula, plus 2AB plus B square. Okay? A square minus 2AB plus B square. Okay? Yeah. So these two formulas. All right. After we apply these two formulas, now for this expression, we can do cancellation, right? The same denominator, the numerator part, this one cancel out. 5, that 5 cancel out. 2 times root 5, negative, plus, so 4 root 5, 4 cancel out, so you have root 5 left. Root 5, this root 5 cancel out, so you get a 1. Okay? So F2, after some algebra calculation, you also get 1. That's the same as the, direct calculation. 0 plus 1 equals 1. So that is correct. F2 is correct. All right, so we practice F2. Next, I want to practice another one. A little more challenging. Yeah, but I want to show you how to work it out. Because later, I will give you several exercise questions. You need to do this kind of algebra. Okay? Yeah, hope you practice a little bit. Yeah. All right. Next one, we need to verify this case when n equals 3. This time, more challenging. Yeah. Because, phi to the third power. Phi to the third. Although you know the formula, right? Yeah, here. So you can use the formula, right? How many of you still remember the formula A plus B cubed, A minus B cubed, right? Yeah. I believe some of you, not all, or small portion of you know these two formulas. So you can find from web if you like. But here, I want to use a different method. A little tricky. Some smart way to do it. So I want to show you. Because this way, you need a little more algebra scales. Okay? Let me show you. All right, so now we do verification. The idea, the strategy. Here, we need to apply some special strategy, okay? We notice that the degree is too high, relatively high, right? The higher the degree, the harder the calculation. So for that reason, our strategy is reduce the degree to make the calculation easier. So that sounds simple, right? But the problem, how do you do it? Implementation, execution. Execution is hard. Even the strategy is correct, but the implementation still very challenging. So let us do it. Okay? Let us answer this question. How to reduce the degree of phi cube? Here, phi is the golden ratio. Golden ratio has many nice properties. So we need to use the properties of the golden ratio. So before we work on this expression, I want to, recall some properties, simple properties of the golden ratio. All right. So we will see it. All right. So first, let's do some simple work. First, phi cube, can we split it in this way? Phi times phi squared? Yes, we can. We want to bring down the degree. When we do this way, we have chance to bring down the degree. Why? Because we single out that phi squared. For the golden ratio, is the phi squared can be represented by some lower degree expression? We need that property. Okay? So let me show you. Phi is the root of this quadratic equation. So that's the equation. We calculate the golden ratio. Okay? So we bring it back. And we can plug phi in this quadratic equation. After that, so we move terms left and right for some, equivalent expression. So the first equation, we can get this. Okay? Phi squared at the left-hand side, phi plus 1 at the right-hand side, and they are equal. This means whenever we see phi squared, we can replace it by phi plus 1. Right? Here, we see this phi squared. Can we replace it by phi plus 1? If we replace it by phi plus 1, we reduce the total degree, right? So that's the property we need to use. Okay? All right, but we have another property also very useful, so we want to leave it there. Later we will need it. That one is left-hand side, we put a 1 at the left-hand side. The remaining terms, the right-hand side. Okay? Why this is good? Why this is good? Because 1 is very special. 1 is a special number. 1 has many nice properties. So if we can represent 1 in terms of other terms, that is a good thing. So later, we may need to use it. So you will see, next step, we need this property. Now we are ready to simplify phi cube. Okay, all right. So we replace phi squared by phi plus 1. This time you can see the total degree is reduced from cubic to quadratic. Reduced, right? The question is, can we reduce it furthermore? The lower the better, right? We see another phi squared, right? Can we replace the phi squared by another phi plus 1? After you do that substitution, you get 2 phi plus 1. Okay? Now, we are satisfied. Because the highest degree here is 1. That is good enough. Okay, we cannot reduce it anymore. Yeah, we cannot reduce it anymore, so we leave it there. All right. Yeah. Next, we want to look at the second term, 1 over phi cube. Now, this time the trick, the phi cube. Yeah. Most of you feel it's hard, yeah, because the cube is at the bottom. How can you do it? Okay, the numerator already lowest degree, right? 1, it already has the lowest degree. How can we do it? 1 is already the simplest expression. How can we do it, right? Yeah. Now, look at the second property, this property. Look at this 1. Now we need that 1 expression. Okay, now it is useful. Yeah. So you can see if we replace 1 by phi squared minus phi, what would happen? Okay, let's do that. Okay, so numerator is more complicated, right? It's okay. We don't mind. We can make it more complicated if we like, right? It is not illegal. It is completely legal. Okay, so but if it can help us solve the problem, it's good. Okay, why after we make it the denominator, not denominator, after we make the numerator more complicated, what's the benefit? Because this time the numerator denominator have a common factor, phi. We can do cancellation, right? We can do cancellation. Let's do the cancellation the first time. After cancellation, we get this. Okay. Still not good enough because phi squared at the denominator. Still not very convenient. Although for some of you probably, if you can see something special, you can already solve it. Yeah. But I want to go to another step further. All right? Yeah. Now, you see this 1 again, right? Minus 1. Can you replace that 1 by this expression another time? Right? Yeah? In terms of phi, right? Phi terms. Because after you do that replacement, you can do cancellation another time. Okay? Yeah, so that's why we do the replacement substitution. After simplification, we get 2 phi minus phi squared in the numerator. So this time you can do cancellation another time. After cancellation, and we write it into 2 terms, 2 over phi minus 1. How about that? Now we get this expression. Okay? We want to add these 2, that is, we added these 2 expressions, plus 1 minus 1 cancel out. Then it is very simple, right? Plus 1 minus cancel out the remaining terms, very simple. Yeah. So let's do it. Okay, phi cube plus 1 over phi cube. This time, after we factor that 2 out, parenthesis, phi plus 1 over phi. Okay. So then if we go back to the Fibonacci number expression, we will have f3 equals 2f1. Yeah, so yeah, because if we multiply 1 over root 5, also 1 over root 5, so this one is f3, this one is f1. Okay, phi 3 equals 2f1. Okay, then equals 2. So in this way, we know, because we already calculate, okay? We already verify f1 equals 1. So 2 times f1, 2. Okay? So we complete the verification in this way. In this way. Okay? But in our calculation, we use some nice properties of golden ratio. And we use some tricks. We use some smart tricks in this one. Yeah. Here, I just want to use this example to show you using the mainly these two properties of the golden ratio, we can simplify many complicated expressions with golden ratios involved. All right, so that's the C.2. Yeah.